like, I know it's the end of the day, and I know people are tired and or jet lagged and or like warm because this room is warmer than the rest of this conference center. I think it's me because it was also you. Yeah. No, but I was also no. Sharad agrees. It's hot in here. It's hot in here. It's hot up here. Okay, guys. Thanks. Sorry, but in another life I would have been an elementary school teacher. Okay, so this is welcome to the second part of the Algorithmic Fairness Workshop tutorial, which I, J.B. Morgenstern, along with Rachel Cummings, both of us are professors at Georgia Tech, will be presenting. And you can definitely think about this as sort of asking when some of the assumptions that Sharad's talk sort of took on faith may or may not hold in practice, and sort of what that might mean to a technical audience who's thinking about designing these kinds of systems. And I do think that there is a place for computer scientists thinking about like, you can use blank word in machine learning, at least in part because we understand like the scale at which some of these machine learning methods are being applied, and that they are being applied in settings where we don't necessarily have huge amounts of data, and we don't necessarily have the ability to sort of say, here's a longitudinal study where we have so much data that we can say precisely what's going on, look carefully into whether there's discriminatory behavior. So that's sort of pushing back a little bit against the idea that computer scientists may not have so much to add to this conversation. So I do want to think about, many of the people in this room are very aware that machine learning algorithms are being used really pervasively, right? Like, it's not just that we're thinking about recidivism tools or risk tools, but like so many companies are saying, we do machine learning for X, and that is like their mission and the way they are intending to make money, right? From companies that are thinking about using machine learning to help craft hiring ads or decide who you should bring in for an interview, to settings where we're all shown advertisements all the time, and a huge number of those are being at least in part selected for you as a function of some of the data that like the ad server has about you, right? Where everybody's aware that this is like some fraction of the content we see online is provided to us because there's a huge amount of information that the content providers have about us and are trying to match us to some of that content, right? And search suggestions are another example, right? And unlike settings that Sharad talked about, these sort of have more complicated intricacies and feedback loops that make the problem somewhat more complicated. I will say recidivism is one of the many settings in which machine learning and or risk tools are being used, although we won't particularly focus on this. I do think that like Sharad is much more the expert in terms of what's going on in terms of boots on the ground for recidivism tools. So I will leave that there, but we're certainly happy to talk about that. Oh, and side note, we made like half as many slides as Sharad, so ask us lots of questions. We know EC's question format, maybe epsilon better than he does. Okay, right. So I think computer scientists, one of the questions that I get on a regular basis when I make any kind of presentation about questions of bias or fairness or discrimination, all the set of words that are used in machine learning, people ask like, what is fairness? Like, give me some constraint or give me some definition, then I will satisfy it, right? Just as Sharad was saying, like, equalize false positive rates, I will satisfy that subject to some, while I'm optimizing some other objective function subject to that constraint. And I think that just as Sharad said, it sort of elides a lot of the important points, and it allows weird gaming behavior, and it doesn't take into account like more important context-specific information. But I do think it is interesting to ask, some of these constraints we're thinking about, like what would they do to interactive learning protocols? Okay, so and just one like further hedge is that like I'm a computer scientist. I may have a doctor of philosophy, but I like don't really know any philosophy compared to like someone who's actually a philosopher. So it's important that we as computer scientists don't run too far afield of like what philosophy, econ, social science, and statisticians think, right? And it's important that we continue to have conversations with people and practitioners who actually think about these things on a day-to-day basis, rather than just like running off in our own tangent away from like whatever they do in like one vector that we think is best. Okay. Yeah. So I'm going to hand this over to Rachel. We'll attach this. Oh, working. Good. I was taught this trick. Yeah. Success, hopefully. Yeah. Good? Is it working? Okay, excellent. Yeah, so to sort of pair into what Jamie was saying about the difference between philosophers versus computer scientists, is that we ultimately are computer scientists and we have a very specific toolkit to bring to the table. We're really good at like optimizing things subject to constraints. And so like here in this fairness space, we should use our tools to the extent that we can. And so today we're going to talk about like various ways in which you can optimize various objectives subject to fairness constraints. But I think it's also important to acknowledge the fact that we're not philosophers, we aren't legal scholars, we personally are not social scientists, although I'm sure in this room there are some. And so in doing this, it's important to have those conversations across department lines and across field lines to really make sure the constraints that we're optimizing with respect to are sort of the right ones in practice. And so this is a part of like Shroud's talk and for that application. And so just as a roadmap of what's to come, you saw today part one. And today we're going to talk about some challenges into the model that was presented before that can arise in practice and in different applications. For example, if you have small amounts of data, if you have feedback, and also if the people providing you data have incentives, and some challenges that arise in that space. And I'll also say, because this is a growing field, we don't really have all the answers yet. And so we're not going to today tell you how to solve these problems. We're going to tell you that these are problems and some challenges that arise that we hope, as a result of this, people will start to think about solutions to these problems. Okay, so more specifically, we're going to talk about 3 different challenges in this space. The first one is if you have a very small sample size. And so that means that we're going to have this imperfect or a very poor model of like estimating a person's risk conditioned on their attributes that you observe. I will also talk about the fact where you might have only partial feedback. For example, you only see whether or not a person reoffends if they get out of jail in the first place. And then we'll also talk about incentives and when people can sort of gain this feedback loop. So I'll give sort of like pictures of these 3 challenges just to really illustrate, and I'll then talk in more detail about these and pass it back to Jamie at some point. So the problem if you have very small amounts of data is that really we don't have enough data to like truly estimate these things. And so you may have like a whole bunch of features and a very small number of observations relative to those features. And so this is a case where you want to do something more than just say pick one threshold, but if you want to like regress on a bunch of different features to decide how to label a single person, you may not have enough data to really make those inferences. And so instead, you're going to have to take some like very large, complicated data set and pick some like very simple parametric model that you can use in which to assign labels to people. And so the question is like, how do you pick this model as a function of your very small amount of data? How do you train this classifier if you don't have enough observations? And there's also a challenge in thinking about feedback here. And so in this world, we have a database, and we plug it in, and we get a classifier, and we label people. And that's a static version, and things are pretty simple. What happens if there's feedback?
And so maybe I'm going to first have a very small sample, I'm going to learn from it, and then based upon things I learned, I'm then going to go back and collect more data. And so this is like saying I'm going to observe the actions of like 10 people who were released from like prison, and I'm going to see if they reoffend, and I'm then going to decide who I should release next time. So now you're no longer getting these like IID observations, and you also only see feedback from those cases where you're labeled in a positive way. And so you don't see the true observation of the people who are not released. And then finally, incentives. And these jokes were made by Jamie, but I 100% endorse them. So now if you have this case where people can also game this like feedback loop through some effort or through strategic manipulation. And so if you guys watch Game of Thrones, these guys are your more like strategic adversaries who are trying to like change global outcomes. Or you might have a person who is like curious but honest, I think is the like a security term for it here. How a person who just wants to be admitted into college and she's willing to go that extra mile to like change her personal label. And so this can also affect the sort of like efficacy and the fairness of your decision making is when you have players who can game this feedback cycle. Any questions about the sort of high level stuff before I go and talk in more detail about these cases? Cool. Okay, so now go through these three different challenges. And the first one is when you have limited data to learn in the first place. And so for example, I think this is the same as the next slide, right? Okay. And so for example, if you have like 20 binary features for each person, that means that to have one observation of like every single type of person, you need to have at least 1 million data points, and that only gives you one observation. And so this means that we really can't say I'm going to learn on like every single possible type of person and on every single realization of these variables, but instead I'm going to have to pick some specific model that can reduce the like size of my feature space. And so in part one, we assumed that you knew the true risk, and so you know the like probability that a person was going to reoffend. Or no, this was for the contraband case. The probability that they had contraband given some like observable attributes. Or in the prison case, Y can be the binary label of whether a person would like commit a crime again if they were released. And so this is really hard for a lot of reasons in practice. If you have a very large data universe, for example, if you have a whole bunch of features. And it's also hard if you don't have like IID data for all different realizations. For example, if you have like high dimensional feature space for each individual, you may collect more information on certain groups, on certain subgroups, and so you may have like more accurate estimates for some groups over others. And there's also other like challenges in practice, which is if you're doing this for like 1 million different people, maybe you don't have the like computational time and space to really do that, and also things may change over time. And so maybe you do have a whole bunch of data, but it's from arrests in the 50s, and so our population has changed, and we understand that like causal factors may change, and so you may only want to have the most recent data. And so for example, if you want to like start from scratch with no data, then you have nothing, then you can't even begin to guess this. And I had the example before how if you have 20 binary features, then you need over 1 million observations just to have one observation for each type of person. And of course, in practice, most things have more features and they're not binary. Things can be continuous and they can be high dimensional. And so this is like a very practical concern. For example, the Compass software that was talked about in the first part of this had 137 features. And so that means that if you want to have even like one observation of each data type, then you need roughly like 2 times 10 to the 41 distinct examples. And that's not something that we can reasonably expect to have.
This was my year too.
Is it a joke? I don't even think it's a joke. I mean, we do have very high incarceration rates.
They only use 6 features.
6?
Yeah.
Okay.
This is widely misreported number.
Okay.
Okay. Good to know.
Yeah.
Okay, and so
Still
now,
hard- Still hard to estimate though.
yeah. And so now bringing this back to the fact that this audience is primarily computer scientists, mostly. We have some tools to address things like that. We think about sample complexity, and we think about how can we make a good decision if I don't have enough observations to make like a full estimate. Maybe I can have some like a partially informative estimate with a much smaller observation size. And so for example, maybe I need like 2 to the 20 observations if I have these 20 binary variables, and so that requires exponential samples. What can I do if I just have a polynomial number? And of course, a real normalization of this will depend upon the like actual problem specification and the model. But I think in general, this is a question that we, as a computer science community, can address, is to figure out how accurate can we do with a reasonable sample size. And also, like, how can you trade off variance versus accuracy? Of course, if you have a very small sample, then you're going to have really high variance. And so maybe things are being like unbiased, we have a really high variance. And so there's certainly a trade-off to be made there. And of course, there's this other issue about the fact that you may have like a different accuracy on different subpopulations. And so that itself may lead to additional unfairness because I may have more data about one group and therefore be more accurate in my classification of them. And even if I'm being unbiased on both groups, that may lead to higher false positive rates or false negative rates across different groups, and that's one type of unfairness. And there's also this challenge of model complexity. How should we pick this model in the first place? And so a few slides ago, I showed like a picture going from a database to some classifier to some labels. How do we pick the right model in the first place? And so of course, if you have like a simpler model, maybe you just want to do in your classifiers. Well, then that requires fewer samples. But if your simple model class doesn't match data, then you're still going to have this bias or this error. And so this is also a question of those design and classification models of what's the right parametric class to use, again, based upon the context and the problem formulation. And if you choose different models, they may be biased towards or against different groups as well.
No, I was just wondering if you have examples for illustration.
Yeah, I mean, so this is a nice one, is that maybe I want to have a simple, classifier. And I guess actually the example from like part one of the talk was nice, how if you just classify someone based upon their Compass score in a gender neutral way. And so if you exclude like a gender as a feature, this means that you're going to be treating different genders differently. And so the choice to not include that as a feature, to include in your model, means that you're going to be treating different groups differently.
Or you could analogously imagine that like some population has a great representation as a linear function of the set of features you have, whereas another population you need, I don't know, some kind of quadratic representation in the feature space that you have observed.
Yeah, the same feature.
Yeah. Or you might need different features. Yeah. Both of those fall in this category.
And I'll also give a plug for Jamie's paper on fair PCA, showing that if you do PCA on the entire population, this will give you very different features than if you do it across different subgroups. If you want to say anything more, make sure paper like you know better.
Yeah, I mean, I guess it's not so surprising, right? But like, different populations have different distributions over the set of features you observe. So if what you do is like a standard dimensionality reduction technique like PCA, you'll see that you have much better reconstruction error for some populations than another, even if the two populations have the same size of your sample set. And so it's interesting to ask, like, if you're picking features or you're picking subsets of features, it's not clear that like the idea that Sharad mentioned, where like there's a fixed set of features which map to a fixed set of risk scores, necessarily like maps to the entire like pipeline that machine learning people are used to thinking about, which has all of these different intermediate steps that have like different decisions that are being made sort of throughout the process, including but not limited to feature and model selection.
Can you clarify one thing, because that seems to contradict a little PCA in a way. Two populations have small dimensions, and there are only 3 and 4 dimensions. If you use a 7 on the overall, you should find back these 3 and 4, and perhaps the 8 one to distinguish them.
Yeah, I guess it's a question of whether you, right, yes, but if you only tried to use 3 dimensions.
Yeah, of course.
Yeah. Anything else on the limited data?
Are you suggesting that you may want to treat the protected features differently with respect to what I mean? Because you can, if you just treat it like any other feature, then it's different from, why don't we just separate the model into the model for conditioned on the protected class versus not, make the different outcome of the protected class.
Yeah.
Are you saying that?
I'm not taking a stance on that. I'm more saying that like these are questions that like if you're asking yourself while you're making your model, like they will have different implications for the sort of classification rates and error rates and all sorts of other different things that you'll see on different populations, and that it's important to grapple with that.
And also, Jason, there may be other there may be other features that are like correlated with these protected attributes, and so just handling like a protected attributes in one way and then a bunch of other features differently, and you may not know a priori which other features are like highly correlated with their protected attributes. Especially as we move into this like, big data era where we just like take very large data sets and plug them into deep neural nets and don't really understand what are the important features of our data in the first place.
I guess all that I was saying was you can imagine a family of models where they didn't impose constraints across protected groups in a way, which means that you can never use one group. Basically, you're required to do them separately. And the model would just tell you that, right? Because the model would have all possible combinations of things across the two groups. So you can imagine models that sort of partition across protected groups in a way.
If they were given
lose a lot of expressive power if there's lots of ways to slice and dice your protected features.
Right. It will depend upon like whether those protected features are available at the time that you're predicting, right? And it's also a function of sort of what set of models you're learning amongst. Right? But I agree with you that like it adds that possibility or complexity if you're allowing yourself to like use those sensitive attributes as features. Yeah.
So next let's talk about this feedback model. And the challenge that in a lot of applications, you only see feedback from examples that were previously labeled as positive. And so this includes sentencing. It also includes like loan applications, because they only see if you are going to repay a loan if I give you a loan in the first place. And so you don't collect data on those individuals who were labeled negative in the first place.
Or another example is like ads, right? We only see whether someone clicks on an ad if we show them an ad. And I think like it's important to like keep drawing on like some of these examples that like we're super familiar with, right? Because we know this example particularly well. So it's like useful to keep thinking about that. It's also a setting in which we might have 137 features
Yes.
that like describes a person.
A whole lot more. Yeah. Although there we also do have a lot of data as well, so maybe. And so this is the case where you only observe the Y for the label of a person if you label them positively in the first place. Or perhaps there's some like weird proxy feedback, how you don't actually observe the true Y, you observe some Y prime that is like correlated with or a function of Y, and hopefully they're pretty reasonable. And so back to the like prison sentencing, you want to know if someone will like recommit a crime, and so that's their Y label. You don't exactly observe the Y, but rather you only observe if they are caught for committing a crime. And so that's your Y prime, how it's sort of a proxy variable. It tells you something, but it's not necessarily exactly the same as the true Y you want to observe. Okay, oh good, I'm getting ahead of myself. Yeah, so these are the same examples I gave before, like prison sentencing, loans. I don't know what this is.
I know. I understand that. That was like my mistake.
Is it a typo or is it a joke?
It is a typo, yeah.
Okay.
So you know, the idea that like, as Sharad mentioned, there's this omitted variable bias, this idea that like, you know, we are very unlikely to see the full set of features that were given to the decision maker at the time of decision making. So like, you know, it's not going to be necessarily possible for us to like evaluate a model as a function of those features, which might mean we have a hard time even evaluating whether the set of examples we have are representative of the distribution overall that we might care about. Sorry.
Yeah. I think actually this point is really important too, which is that we're not just getting limited feedback, we may also be getting biased feedback. And so we typically use things like, you know, arrested or found guilty as proxies of committing crimes. But we know things don't happen in a vacuum. And so there are like other things correlated for the person being arrested or being found guilty, for example, race. So we know that there's lots of other challenges and perhaps biases in the context of the feedback that you get. And so it's not just that you only get the feedback of the positive examples, it's that you're also getting this like potentially biased feedback, and the bias may be very complicated and hard to like quantify. Well, the nice thing is that as computer scientists, we know how to handle this. And this sounds to me like a Bandit problem. I have to make a decision, and then I get partial feedback. Great, we have a ton of algorithms that can do this. That should be fine. What's wrong with it? Is it really, at least applications that we're talking about in like school admissions and in prison sentencing and in loan applications and in drug trials, people's lives depend like really critically on the decisions that you make. And so necessarily, explorations, bandits, tells you you have to like do the wrong thing for a while until you learn. But that exploration can be costly and perhaps even morally questionable. For example, it might tell me I have to collect more data on a certain population, and my prior tells me this prisoner is likely to commit crimes again, but just to explore, I'm going to release them and see what happens. That's what bandits tell us. Maybe we don't want to be doing that in practice. And the same thing in drug trials. I might say, I think this drug is likely to kill you, but just to be sure, I'm going to explore. we shouldn't be doing too much of this in these practical applications. And so we have all these tools, and we have these like algorithms, but we sort of don't want to use them as is. And so the question is can we do some good exploration and so harness these like Bandit tools without doing things that we find to be morally repugnant? And so I'll pass it back to Jamie to talk about those things and about incentives.
Okay, great. So thanks, Rachel, for that part. As Rachel mentioned, in settings where we really have a lot less data than would be sufficient to say that we have a really accurate model of the thing we're trying to predict given the features we have, standard thing to do is think about Bandit problems, right? But I think all of us, if we were like dying of some disease and we're told there are 5 things that are currently under trial, 5 different treatments that are currently under trial, like we have some estimate of their mean and variance, but we're not going to give you the thing that has, the highest expected life expectancy for you conditioned on getting this treatment because like I actually want to know more about, some other set of features, and so, I actually want to know sort of like how this thing that I think is not very likely to cure you, I want to know for sure that it's not very likely to cure you, right? And so, one of the questions as computer scientists we can ask is like, when might we need less or no explicit experimentation, even in settings where we are making decisions and those decisions affect the set of examples we observe, right? Because the whole reason we were talking about exploration was that it was some kind of solution or technical fix to the fact that we don't necessarily get IID data in all different contexts. So, if we're thinking about it, some very simplistic model where every day we have some information about the set of people we get to assign different drugs to today, and we just want to give each person the thing that like maximizes their expected lifetime conditioned on receiving that medication given all the information we have about them as patients, right? Which like perhaps for individuals, many of the individuals would be happiest with that decision as opposed to being told that like we're randomly assigning you one of these drugs that like is substantially less likely to cure your illness. Then we'll see sort of how those different individuals do under that kind of treatment. And a point I want to make is, if the set of drugs I always want to give the people who show up every day are always the same, right? If I always think that drug treatment A has the highest mean for every person I see in the future, I'm never going to collect any data about person B just doing the greedy thing, right? However, if there is a reasonable amount of heterogeneity in the set of examples we see, right? In terms of the set of different features I see when I'm trying to assign you to one of several different treatments, that might be enough to say that I don't need explicit experimentation built in or baked into my algorithm, right? But this is definitely something you would have to check for your particular application and the particular set of algorithms you were thinking about. But I do want to give a quick plug to 2 papers that sort of explore this to some limited extent. The idea that if you're thinking about a Bandit context in which you only receive feedback for the decision you make, and you actually do want to do this greedy thing where you like on day T, you're not actually sort of thinking about your long-term learning rate. You just want to guarantee that you're doing the best thing for the person who arrives on day T, but you also like to say separately that that will give you some kind of like convergence. You can do that under certain assumptions about the distribution you have of the set of people you will see, as well as the set of like as well as sort of the efficacy of the 2 different treatments you might be choosing between. Grant, yeah.
This is maybe like an annoying conflict.
That's
One of this seems to have some relationship with the social learning stuff that would be presented later in EC, and also like in practice the way people deal with this, I think, is that they don't have the feedback loop, right? So if I have a clinical trial, I'm going to get a lot of data at once. I'm not going to tell you how the first 5 people turned out until I have all 500 samples in. And then I release that because otherwise it's extremely problematic.
Right, and that may be a more appropriate solution in some contexts, right? Basically removing the fact that like we might be getting non-IID observations, right? I think that there are contexts in which that is appropriate, like at least if you look at like the frequency with which people at EC Union, like the machine learning community, write papers about bandits, like there is some thought that there's some traction to thinking about algorithms that do some kind of exploration trade-off and maybe do use the exploitation rounds as data to update their models.
And I will say, even in the case of these trials, they do look at their data in the middle, but they just have to like pre-specify at what points they're going to do it. But it's actually like a very like important part of the drug trial process, because if you find out after like a month that your drug either works like extremely well
Or it kills people.
you want to stop the trial in both of those cases. And so they do have these like pre-specified points at which they're like supposed to peak at their data. And so there is some feedback, but it's more like 2 or 3 points instead of a whole bunch of abandoned.
Can you clarify?
Oh, sorry, she had her hand up first.
So just as a representative of Bandit community who writes a lot of papers, I just wanted to add so if you have diversity within your distribution and if you are using a prior and using information gradient, you would automatically not explore because you have already information in your direction. So I don't know will it really, it's not like you're not taking into account that you have information in certain directions. And also it's also a matter of perception versus actually doing the right thing. So sometimes when you're exploring in certain direction, it's not like you're not doing what it's best. You don't know what's
Right.
best.
Yeah.
There
No.
is no information.
Right. Although you may or may not have like means which are close to each other, right? So I totally agree with you that the way you can phrase picking something with a lower mean but higher variance or lower mean and lower variance, like it's not clear that what you're doing is better or worse, right? But I think a lot of people think of like the greedy decision. If this is the only decision I'm ever going to make, and these are the 2 examples I have, right? Or these are the 2 decisions I have. Here are the means, here are the variances, right? I agree with you that it's not correct to say that like the better thing to do is to make the decision for like whatever has the higher mean, but like some people think that is the right thing to do. Yeah, Jason.
Could you define some of these conditions?
Yeah.
I don't know what
Yeah.
certain points of some variety means, and I also don't know what few points of some other words mean.
Yeah. So in the context of our paper, for linear rewards, what this means is we basically want there to be a good amount of thickness in every direction, right? So like conditioned on you being above some linear threshold, we want there to be like large eigenvalue, right? Large minimum eigenvalue, because that means that we're basically conditioned on us thinking that you should get treatment A, like you're probably going to have a wide assortment of different sets of features, so I will get a reasonable amount of information from you, right? So that's like one of the things. The other condition that our paper uses asks that so that's sort of like a covariance, conditioned on you being above or below some threshold in some space, like there's still a lot of variety in terms of the points that land on that side of the decision boundary. The other is, if I think about 2 distinct, treatment A and treatment B, if treatment A is better for you than treatment B in terms of like current expected outcome, I want there to be a reasonable probability A is better by some margin. And those are necessary for 2 different reasons, but like they're necessary. The first one is like sort of so that you always, no matter what decision you're making, are like continuing to learn a better model. And the second one is sort of necessary for low regret in the sense that like you only need it depends a little bit on what exactly your model is for learning. But like the second one you might need basically because like if 2 things have very, very similar reward, it's much harder to get low regret. Does that satisfy you for the moment? Okay. All right, great. Good. Yo, yeah.
Just one clarification. So the algorithm is greedy. That's supposed.
Sorry, can't hear you.
I'm saying I just want a clarification. So the algorithm is greedy, but then you need to update, I guess, your belief in a way that is taking that into account.
Right. So what I mean in that context is like the simplest, I don't want to use the word stupidest, algorithm that one could design, which is the following. I have 3 treatments, and I'm learning linear models for how these do as a function of the set of features I have, and I'm using each example I see as like, I pretend it's IID, and I just have some observation matrix that I use to estimate the linear coefficients for each of my different treatments.
Oh, you're not even taking into account.
Not even taking into account the
That's
fact,
enough.
assuming the set of conditions that I mentioned. Yeah, and that in general is not going to be true, right? So I imagine a bunch of you are familiar with this, and like it's not hard to pick up examples, but like you're unlikely to get a low regret algorithm that does something like this, right? Make some decisions, get some examples that are a function of the decisions it made, uses those examples as though they were IID data, and then like it's relatively unlikely that's going to work well unless you have some pretty strong assumptions about the data and or the algorithm you're using, right?
And you assume you know this gap. Anyway.
Question. Well, so I think your learning rate will depend upon it, as opposed to you needing to know it explicitly. Now, it's been a while since I like opened up that PDF, but I'm pretty sure that that was the case. Okay. So the last point we want to make, and we're even going to get you out early, so you're welcome. I don't know. I'm tired, but I'm coming from the West Coast, so. And apologies for this image. It's going to show up a few different times, and it has almost nothing to do with what I'm talking about here. But I think the point of it, when I made this slide, was the idea that like it's going to be really difficult to understand what is going on with some of the different machine learning models and settings in which machine learning models are some part of a bigger set of decisions and interactions that are happening between a bunch of people, especially if those people care about the outcomes of some or many parts of that decision pipeline. And so this picture is like the headline page from a different ProPublica study, where what was shown was that like if you conditioned on a person with like a very similar driving record who lived in a predominantly white versus predominantly minority race community, even conditioned on like the rates of car break-ins and various other kinds of things that are expensive to car insurance companies, that the minority communities are given higher insurance premiums. And so like Sharad looks like he has something to say to that, which is certainly possible.
I mean,
yes, I'm saying.
Yes, this study has been debunked. I would say.
Yeah.
But it's a concept, I think.
Yeah. Right, but it's like, it's interesting to ask, like, you know, in what contexts where there are a huge number of different people who have different incentives, like what those incentives will do to different equilibria of some game you've put together, right?
The graphics here kind of look like the graphics in the other paper we talked about earlier did not agree with the conclusion. So that's sure I'd look. There was this paper about
Compass, yeah.
You had this paper that you talked about how something is biased. It says that something is biased against blacks, and you didn't agree with that. And it kind of looks like the same graphics.
Yeah. ProPublica has like a
for two.
Yeah. ProPublica has done a number of these studies, and I think part of the problem is like, you know, there's not a great amount of communication between the PR on this, the technical practitioners, the statisticians. Like there are a bunch of people who are like not great at communicating amongst each other. Like one of the divides is between computer scientists and the practitioners, but another divide is between like the people who are writing about all of these different things. And I don't mean writing in like a technical paper sense. I mean writing sort of more pop science kind of coverage, right? And has different implications, certainly, that are worth considering, right? And I won't name names, but I think a quote that I liked was, we should be a little bit careful when we go around like calling Google's, advertising engine racist. That might make everything harder for us, like in terms of our ability to interface with them, see what's actually going on, and like have a meaningful conversation that actually affects the outcomes we might want to see, right? And that was a technical person who said that, right? But the idea that some of these, both pop culture, but also some of the flashy ways we can express some of our technical points can be counterproductive. Okay. Anyway, largely debunked. However, like they have one person who takes all of these pictures of these like of people in a very particular context that like all look very distraught, right? So, okay. So I do want to briefly outline, because this is EC, a little bit of the work that has been done, or some interesting directions in terms of equilibria and bias, discrimination, the set of words that we've used that like may or may not have like a specific technical meaning as computer scientists have agreed upon, although perhaps other communities have a more coalesced set of things to think about. And so I want to briefly talk through, I think, a really elegant result by Lily Hu and Yiling Chen. And I think this appeared at that STAR last year? Correct. Okay, good. I'm woefully ignorant of my citations. And basically what they show is there's a setting where you can set up a nice model where basically there's a two-stage hiring game, where if you set up that two-stage hiring game and don't enforce any kind of statistical parity or any other kinds of constraints that computer scientists often call, solutions to discrimination, that many of the equilibria of that game will have outcomes where essentially only one population makes it to the job at Google, right? Whereas if you make some constraint in the first stage of this hiring game, it can lead to Pareto improvement of the set of equilibria, because it will cause, first of all, it forces, it constrains the set of decisions that are made in the first round, and that can also incentivize further effort exertion on the part of participants from multiple different populations, right? So I will say epsilon more about that, but only epsilon, because you guys should go track down Lily and Yiling, and they will give you a much.
They're both here.
And they're both here, right? So how did all this stuff get very stretched? I apologize. I had some PowerPoint issues. Okay, so the broad picture setup of the result they have is we imagine that there's a huge population of people, every single one of whom wants to work for Google, okay? And different people have different attributes that make it easier or harder for them to exert effort and perhaps make themselves more qualified to eventually work at Google and be productive employees at Google, okay? And there may be some relatively small set of people who exert enough effort in such a way that they are observably very excited and have worked very hard in trying to train themselves to be qualified, at least preliminary employees at Google. Also, apologies for the unnecessary plugs for Google, but this was just too easy. You'll see in a second why. Okay, so if you imagine that some company has a two-stage hiring process where they first hire people as interns as a function of the amount of effort they can see was exerted, and maybe other things that people know about them, maybe as a function of their race, their gender, maybe some other things. Then they make some set of decisions, right? And some subset of people get to show their chops at Google for a summer or some other company. Google is just because this actual set of graphics was, I think, targeting Google. So if you imagine you're in a world such as this, and then actually at the internship, what matters is not just sort of how much effort you exerted in college making yourself prepared, but actually how qualified you are, which is a function of the amount of effort you exerted, but also a bunch of other things. And also the amount of effort you exert during your internship, right? So like lots of different points at which you make decisions, right? So you imagine that you've got some intern project and you want to work really, really hard because you want to show that you're a really great intern, so they should make you a full-time offer, right? And then as a function of the project outcomes alone, Google decides who they want to hire as full-time employees, right? So if you have a model such as this, where like there's effort exertion at multiple stages by people who are trying to get this ultimate job, the question is really like, does the effort in the first round cause these people to be qualified for the internship and ultimately the job or not? And that's a function of how hard they work. And so, using some kind of statistical test which might allow for the different groups to be treated somewhat differently may actually encourage more people to work really, really hard in college and be more qualified for their internships, therefore meaning that like more people pass your entire threshold of like highly qualified workers, right? So this is like you can just imagine that like if people have different, if we lower the threshold or we make it a little bit more feasible for some number of people to like work really, really hard and get a job they want, that might cause a bunch of people to work way harder, and all of a sudden we have like an amazing workforce, right? And that's all that this is saying. Their particular model has multiple stages where like there are direct observables and then things that are not so observable. But that's the point of this paper. The main takeaway is like, if the intern hiring is group blind, if I don't look at race or gender in the model I use, then there are going to be equilibria where like the full-time employees are entirely white dudes. Whereas if you are sort of required to satisfy statistical parity, which I am in no way in general arguing is like the right notion, but it is some constraint. If that constraint is placed on you have to have, statistical parity at the time that you hire interns, what they show is in this model, all equilibria in terms of the full-time employee population also have statistical parity, which again may or may not be what you want, but it is something different that comes out. And furthermore, they show that the equilibria Pareto dominate the other set, right? So somehow by conditioning in this first round on like making sure that both populations have possibility of being considered for an internship, that really like improves the outcomes for the employer, for the employees, and so it's interesting to think about contexts in which the incentives of different participants might suggest you think about some of these constraints, and they may help you, not just like, they may not just be something that you do to like avoid bad press. Okay, so I do want to say just a couple of minutes about risk aversion, and I think a lot of, it's kind of nice, in this community I get to sort of assume people know that like not everyone might be risk neutral, right? Yeah.
Sorry, do you have a comment on the previous slide about what in the model might be driving this outcome? Like what are the key features of the model that give you this?
So there are several things, one of which has to do with the fact that what is being observed and selected upon is like an imperfect proxy for the thing you actually care about. Like Google actually wants to hire people who are going to be very productive, well-qualified employees, but like when you're a college student, like I don't have enough data about you to actually say, like, here's a measure of your quality. Instead, what I see is like, I see you were in debate club, and I see you were like, the president of the ACLU club, and I know that you like won this programming contest, and those things are like some imperfect measurement of a combination of effort and qualification, right? Basically, the amount of effort you put forth will affect the probability you're qualified, but I only get an imperfect observation. That's definitely like a big part of that driving thing. Yeah?
No, I just want to answer to Jason that there's another ingredient, which is that there is a preconceived belief that some people in a group will be more qualified, and that automatically generates a vicious circle. But if you don't have this belief in the first place, you don't have this. That's
so
one
this,
ingredient.
yeah, so for this paper, there's not necessarily a baked-in idea that there would be some taste for discrimination.
No, it's.
No, but
it's
the
not
prior
case.
is the,
It's
is
just
it
a
group
prior.
A performs better than group B?
Yeah, there's a prior belief in the population, and that causes this. If you don't have this, there's no.
So it has been some time since I've looked at this paper, but my recollection is that this paper doesn't have anything like that built in, although there is some, there is some reputation. Yes.
That's what I mean.
Yeah.
Okay, yeah. Okay, so like it's,
There's a perception that group A will perform better if you hire them on average.
It's a reputation that is not rational. There's no reason for that reputation. It just comes
Yeah.
from.
Yeah.
But
And so-
it generates the insight.
And so really what happens here is because you have this like a two-stage game,
Yeah.
if you enforce parity in the first round, it allows individuals from that group to send a signal of their high quality. And so then that sort of allows this prior to be updated, and then that yields more fair outcomes in the,
or more diverse outcomes
Yeah.
in the later outcomes. Yeah.
So important for this model to be, for this result to be interesting. So you're saying, I mean, I think if there are two groups, the skills have to be IID across the groups beforehand for me to
Yeah.
care about this,
They are.
Yeah,
right?
yeah.
And so that because of that, if I don't have both groups in the second stage, then I'm not being efficient because I'm not getting the best people, right?
yes,
Yes, but there's a
there's also
repercussion.
this feedback loop where, but because you give people the possibility of being hired where they wouldn't, and that causes them to work harder, and therefore they're even better when you do hire.
Right, so it's not quite the case that, I mean, I guess it depends on what you're thinking of as a fixed feature and what you're thinking of as like changing as a function of the effort which is exerted by participants in this setting. But like, you know, basically if I make it possible for a larger subset of people to possibly be considered for this opportunity, in their model that makes it more likely for those people to exert the effort to make themselves more qualified. Right? So it changes the distribution over people who are participating in the labor market. Does that make sense?
Yeah.
Okay, great. And as was mentioned, right, sort of, one of you mentioned something about like, something about like diversity of the set of people we see in round 2, where we actually collect more data in round 2 than we were capable of collecting in round 1. Right, so this is sort of related to this idea that like we have some feedback, we have some limited data, and we're gathering more data as a function of the set of decisions we made before. It looked like somebody, yeah.
I just want to read it, not fat stuff.
Ah, yeah, I think they had something.
They had a fat ML workshop.
That's right, okay, good, yes. Good, yeah.
Yeah, I have a question, not on this, but generally on the job. So earlier, Shabbat mentioned that anti-classification is not a guarantee against stage-based preference. Like, omitting the feature doesn't mean that you're not discriminating.
Right,
But-
and adding it doesn't mean
Yeah,
anything
vice
either
versa.
necessarily, yeah.
So one of the remedies was I mean, in that particular case, gender-based models, which probably relies on the fact that there are robust sort of models which, like that graph that said that for women the repeat offense rate is lower. And then in this part of the conversation, we spoke about how that may have other set of fallacies like limited data. So from a practitioner's point of view, like I can understand that reducing dimensions, the first two fallacies, right? I forget the names. Error
limited
rate
data.
prediction and what was the first one? So there were 3 on the slide. Right? Yes. So those are like you're actively trying to modify the data to in the hope of avoiding taste-based preferences. But if I had to settle for like something, is anti-classification a good enough guarantee? Because I don't know, like
So I think, and I think Sharad might disagree with me on this point, but what a good second approximation is really going to depend on what you're doing. Like, I think what's appropriate for advertising is wildly different than what's appropriate. Maybe he'll agree with that. Maybe this is a sufficiently unobjectionable comment. Like, recidivism, advertising, really different stakes, really different societal, historical, like, structures which are upholding these different things. I don't think there's like a single set of best practices. I agree with Sharad that like having more accurate risk models in general is a good thing, but I don't think that, like, there are some, like, for certain computational reasons in certain contexts, trade-offs one is making between like should I choose a model which has higher variance or more accurate mean, right? And I think like you need to grapple with those questions and ask people who like don't just work on the technical side, but think carefully about the societal implications of those different choices you make. So I'm not going to give you an easy answer of like, just kind of like Sharad said, like there's not a simple statistical test that's going to tell you what's going on in terms of like whether or not you're discriminating, or whether or not you're inadvertently doing something discriminatory.
And I do want to add, there are times when you do want to do taste-based discrimination, and that's sort of what affirmative action is because you're consciously admitting, I do want to treat different groups differently for this historical reason, and so there's times when you do want to use these tools, and there's times when you do want to use other tools, again, depending upon the context and
whether
the implications to the individuals and to society.
Right, and to use some verbiage from the previous part, right, second order effects can really matter too, right? So if we care not just about the outcomes of the set of decisions we're making, but sort of if admitting more people from certain populations means that more people from those populations will like ultimately be college prepared in a few years, that matters, right? And that's different than like just sort of thinking about this decision fixed in time and not having implications for future people who are participating. Yeah.
Can you clarify in that example if you have anti-classification? I think there's no more issue.
I'm sorry to
Wait,
interrupt. Can you move the mic up a bit?
Yeah, sorry.
Good.
I still claim all of these things were meant for like male clothing. Yeah. Okay, great. They were made for male clothing. I'm just going to say it, and someone can prove me wrong if I'm wrong. Okay, so
Where's the example?
I think I lost which thing you're referring to. So you want to know?
So in this example, the Shen paper on the market, if you have anti-specification, don't use the gender at the time in the feature, you will actually achieve the target and failure.
So I think it's reasonably unrealistic to imagine a world where your employee is not going to be relatively confident about your race or gender when they're making a decision. So like as Sharad mentioned, like this idea of just throwing away race or gender and like things that are super strongly correlated with race or gender, you're going to end up with absolutely nothing that you can predict upon, right? And so like I think, if you're thinking about being an honest practitioner, that's a little bit different than if you're saying like, will this, expecting an external model to behave in a certain way, for example, being gender blind. It's not clear that like that would fix it because, they could in theory reconstruct that from other features that they have.
Yeah, of course.
Yeah. And I don't know the answer to the other, the more direct version of that question. So, okay. All right. Yeah.
Taste-based discrimination, affirmative action.
Yeah.
Is that, I don't think of that as taste-based discrimination. So I would say affirmative action, you're just optimizing for a long-term outcome. And so the idea is that it's perfectly profit maximizing to have affirmative action policies. You care, for two reasons. You care about the diversity right now, and you also care about your long-term effects across groups. So it's perfectly rational. You're like not doing anyone any favors. You're just like,
right.
This is a perfectly rational thing to do. In taste-based discrimination, the idea is that you're sacrificing profit because you have preference to discriminate.
Right. Yeah. And I guess there's some question as to like the set of things that we are calling affirmative action right now, which of those we are doing. But
this is a profit maximizing.
Right. This
strategy.
Right, in the sense
It's
that
not
when you
just
take it
discrimination.
exactly, right? It's not even though I think they do make some assumption, as was mentioned, that like there's some different set of priors in terms of like what I believe to be true about the two different groups' reputations.
Which is statistical discrimination.
Right. Yeah.
About this result, what it reminds me of is the result in auction theory, that if you have multiple bidders and you have different priors about them,
You should
you
use
could
different.
increase your revenue by discounting the prior a little bit and sort of evening out the playing field between these guys to drive up the competition. If that's the case, then it's not really, it's not about diversity. You could about evening out the playing field and increasing the competition.
Yeah, and there's some degree to which this has some commonality, right? Like, at least in like my zeroth order thinking about these things, right? Like you're somehow like making people with similar effort exertion levels in two different populations be more competitive with each other is what you're suggesting, right? And so like if you put in 10 units of effort and Rachel puts in 10 units of effort, like maybe those 10 units of effort get you slightly less if I were thinking about my prior over who's going to be more qualified with 10 units of effort. But I should still, there may still be some context in which like, those 10 units of effort should make you more competitive with each other. So, although it's something a little strange, right? Because they're not actually imagining that there's a limited number of slots in either of these rounds. They just like take people above some threshold. And it's only better for them to hire more people in the end. So it's a little different than, I guess it's, there is some relationship though, yeah. Okay, so with the last couple of minutes, I just want to say briefly that, most of the sort of incentive questions that we've been sort of poking at a little bit have been thinking about the incentives of people who are generating your data, who are facing your model. That's sort of the context in which we've been thinking about a little bit of these equilibrium effects. And it's natural to ask whether the people who are building these models may have incentives in some larger game as well. And so, I just want to put as like one brief thing to think about over dinner is the idea that there are, if your person who is designing models is not risk neutral, right? Meaning they don't necessarily have like, they're not equally happy with like flipping a coin as getting the average of flipping that coin, right? That might affect the set of choices they make in some kind of machine learning setup, which would not necessarily correspond to what we think of as like picking the best set of models given the amount of data you have, right? So I want to draw a bit of a distinction between what I call sampling uncertainty and model imperfection. And I apologize to people who have heard talks about things I have done in like wildly different contexts, because this is like a striation that I make because I know a little bit of learning theory. But like the idea that like there's some uncertainty you have because you have limited data, and there's some imperfection in terms of the model you choose that's not a function of like the limited amount of data you have, but that the model itself is an imperfect match with reality. Right? So like I'm trying to fit some linear model to something highly nonlinear. No amount of additional data is going to like overcome the fact that that linear model is only going to do so well in terms of point-wise estimating the things I care about. Okay? And those will behave, those things will affect risk-averse model selectors differently. And if we're thinking about someone who has preference for certainty over randomness, that might cause all sorts of sort of wonky things to happen. So, just think about something really simple where there's some strictly concave utility function that some machine learning model selector has. And all I want to say is that like having a strictly concave utility function might cause a model designer to prefer a population with lower variance rather than higher variance. Right? Even though a population with lower variance, like if we're talking about risk scores, like we do a poorer job maybe being able to delineate them, but we also have a better understanding of what the mean for that population is, right? It might also mean that like someone who's choosing a model might prefer a model that has higher training and test error, but has like smaller confidence bars, right? Just because like they can make some kind of inference about like the tightness of the prediction they're going to make. They may analogously prefer a lower dimensional representation. They may prefer to drop some kind of relevant attribute, right? Which in general, if what you're trying to do is like, if you have a whole bunch of data, right? You presumably want to take into account a whole bunch of different features, right? But if you're risk averse, there are going to be settings in which it's like, well, maybe it's better to like drop this feature. It's not clear how much predictive power it's giving me. Maybe it's even giving me enough predictive power that EC theory would say I should keep it. But like, I'm more risk averse then like, I'm not just trying to minimize my expected error in the future, right? Maybe I have some more complicated set of preferences over probabilities. So, you know, I'm just, the last couple slides, which are just sort of saying these things in more technicality, right? This idea that like, you might prefer to learn over a class with lower VC dimension, just because the variance is going to be higher if you learn over a class with higher VC dimension, right? And again, this is going to depend on how you model the utility of some risk-averse learner, but I think it's important if we're thinking about some kind of model where we have interaction between a company, not like a benevolent agent that we get to see every single decision and every single feature they ever observe, but like, you know, some strategic agent who's choosing some model that we have some limited data about, and those are interacting with other strategic agents. It's going to be important to like account for notions of risk in these contexts with relatively limited amounts of information. Right. And I think that's everything I have. I have one open question. Yes, one open question slide. Good. Okay. So, you know, I think it's interesting to ask about like how one might, intervention is the wrong word, but like, you know, if risk is one of the reasons we see people making some of these trade-offs that don't necessarily correspond to what we think of as minimizing expected future risk as a function of the amount of data they have right now, that's a natural setting in which it might make sense to ask about whether insurance or some other set of like external interventions might cause those actors to behave in a way we prefer. I don't have like huge amounts of ideas in this direction, but I think it's a natural one, right? So like you could imagine the federal government protecting certain kinds of loans in an attempt to see, to gather more statistical information about that would be then publicly available and might change the way different banks have lending practices for different populations. I'm also really curious to know, in a bunch of different contexts, whether we see sort of evidence of different attitudes towards risk. And I agree that large corporate, well, I agree with myself, you'd be surprised. That, you know, if you're a large enough corporation and you've been around a long time and you have a sufficiently diverse set of like markets in which you participate, like maybe risk aversion isn't a great, maybe you probably aren't super risk averse, but like I don't know that we have a huge amount of evidence about that, and like maybe talking to like some economists would be a good place to start in terms of understanding how large corporations deal with risk. And we do know that like maybe there's even like not risk aversion but risk seeking behavior in certain different domains. So I think it's interesting to think about sort of how these different things interact together. So I think with that, any of us are happy to take some questions on this part or the earlier part of the talk. So thanks, guys.
Oh, I was just wanted to clarify, when you say risk aversion, you clarified uncertainty and randomness, so risk aversion is like vector uncertainty. So
I was very vague, and I was vague partially because I want to encapsulate several different things when I say that. So one thing you could imagine is that like there are no features in the world except for gender, but like men have like 0 variance and women have variance 1. It's actually usually the opposite. Like women tend to have tighter concentrations for any like measurable attribute. Second. Okay, so in that context, when I'm a decision maker and I'm trying to decide like should I give a loan to a man, I know exactly what I'm going to get. For a woman, I'll have like more variance, and like even if they have the same need, a risk-averse person is quite likely to prefer the deterministic solution over the randomized solution, right? And you know there are different trade-offs depending. That's sort of like the 0th order, right? Things become much more complicated when you're choosing about when you're choosing different model classes and you have different features. But I think like the point is that like people who think about learning theory often say like, okay, this is like the empirical error I saw, right, of this hypothesis. And And then I know that's, plus or minus some like gamma. I know that like the true error is within this confidence interval with probability 1 minus delta, right? And like, maybe I use like the upper bound on the confidence interval to say like, this is an upper bound on how bad this prediction might be on the true underlying distribution. It's not clear that like where on a confidence interval like a rational actor would behave, right? Like what they assume, right? That's part of what I'm saying. Yeah.
Sorry to interrupt one more time. Can you keep the mic on?
Sorry,
for
I thought we were just answering questions. Other questions? I know it's dinner time. Yeah.
I have a question that kind of combines the two. So when this company made the criteria for whether or not to keep people incarcerated or let them go before the trial, how did they select down to the 6 attributes? Yeah, I guess that's basically the. Or do we know how they kind of decided on these 6 as the relevant ones?
It's a bit of a black art right now. So for Compass, we don't know. For the PSA, public safety assessment, we kind of know. And they're kind of doing something more or less sensible. They take a bunch of features, they fit some regression, they look at the highly, the ones that seem to be quite predictive. They do some rounding of these things, but it's a little bit ad hoc. It doesn't seem terrible. We have a paper that does it a little bit more, principled fashion that optimally balances simplicity with accuracy. So there's a lot of bad statistics that I would say is going on in the actual development of these things with the high level idea of let's use all the information we have to make a simple rule to predict risk and then draw a threshold. That high level idea seems okay, but for example, even in Compass, we were able to do slightly better if we use a nonlinear model, use their scores plus some additional information, we could eke out a little bit more performance. So and that's also what makes people feel a bit uncomfortable with Compass, is that they're not transparent about how they're doing it. These more modern companies are possibly, because of public pressure, are being more open about it.
Right, and actually to make a plug, which is related to something Sharad said in his talk, but also just like maybe a political statement. Perhaps the worst of all worlds occur in settings where it's not just like a private corporation and it's not just like the federal government or the state governments, but it's like some unholy marriage between the two where there are like legal decisions or like something like legal decisions being made about people who don't get to choose whether or not they're participating in that process. And there's some like profit motive, which is incentivizing like keeping things as black box as possible and revealing as little information about like the data and the models that are being used as possible. Like that, from my perspective, is like the most dangerous setting we could be in terms of ability to understand what's going on and if there is a problem. Right? Not to sound too like political.
Is recidivism backstabbing?
Sorry?
Sounds like recidivism is backstabbing.
Well, they do publish their criteria though. I mean, there's some cases like with I think New York City, like teachers where they're rating the quality of the teacher, and it's just a black box. Like you don't know what goes into this thing, and this affects whether or not you get tenure or whether or not your pay goes up. And it's just like some company just says it.
Yeah, and I think like both black box models and even models where they show you what they're using to predict, but they don't tell you why that is like what data set they use to generate that model and like, what features they originally had and then pared down to this set. That seems much more problematic, right? And freedom of information requests only get you so far, and so like it's particularly difficult unless you can like convince them to talk to you. And certainly if you're someone who's incarcerated, you have relatively limited ability to like get that kind of information. So. Okay. Thanks,
All right, thank you everyone so much for being here.
Yeah, thank you.
Thank you.